Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and today I'm going to cover the length of a smooth curve in 3 space. So, if I give you this vector valued function r of t, which is defined by f of ti plus g of tj plus h of tk, where f, g, and h are differentiable functions on some interval I, then the length of this curve on I is computed by this thing right here. It's going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared with respect to, the parameters t. Now, this is really just a direct extension of what you've seen in Calculus 2, where we were finding lengths of curves in just 2 dimensions, but, this h of t wasn't there. So since we're in 3 dimensions, we have, that third component. And the way we explain how this is done is, if I want to find the length of this blue curve, what we can do is we can partition this thing, and let's say this is A and this is B, for instance. So if I'm going to go from A to B, now this would be t equals a to t equals b. But what I can do is I can slice this curve up like so. And the way I can find its length is I can estimate it with a bunch of straight lines. So straight line, straight line, straight line, straight line, and so on. Now, each one of these straight lines would look something like this. And if I want to find its length, well, you know, um, these things are going to be defined through, the functions f, g, and h. But if it was just in 2 dimensions, like this would be the x and this would be the y. So what we're going to have is we're going to have a bunch of Pythagorean theorems. So in 2 dimensions, it was really easy because I'd have like an a squared plus b squared is equal to, c squared. Or, c would be the square root of these things. Now, in 3 dimensions, I've extended it to 3 dimensions in a previous video to show you that Pythagorean theorem works in 3 dimensions. And that's really what we have here, is that, this is going to be, f prime, this is going to be equal to g prime, and then, this thing would be equal to its length. So this would be equal to the c. So I could say its length is going to be the square root of, f prime squared plus g prime squared. Now, I'm not trying to do too much hand waving here. I've explained this in detail in Calculus 2. I'm trying to just show you that this extends to Calculus 3. So, really what we can think of this as is the summation of a bunch of these Pythagorean theorems. So what we're going to do is we're going to slice this infinitely from a to b. That's why we have differentials as opposed to and integrals as opposed to summations. Okay, so let's use this to compute a length of 2 curves. So this example, I want to determine the length of this vector valued function, and I've given r of t is equal to 6 sine 2ti plus 6 cosine 2tj plus 5tk. Now, even though its geometry or its shape really isn't going to help us find the exact length of this curve, it's beneficial for students to kind of understand, like, what does this thing look like? Now, if I was only going to look at, say, this part of it, if I was in 2 dimensions, we'd be talking about, looking straight down, I'd have some xy plane. And these functions should look somewhat familiar to you. Now, if we had, say, our unit circle that looks like this, what I know is x would be equal to the cosine of t, and then y would be equal to the sine of t. So, I could write this function as r of t is equal to, the x coordinate I plus the y coordinate j. And if I went from 0 less than or equal to t less than or equal to 2 pi, well, then that would draw the entire circle. Now, if I went from 0 less than or equal to t less than or equal to pi, what we're going to do is we're going to draw from here to here, only the top half of that circle. Now, even though this doesn't have the cosine function in the first coordinate, the sine function in the other coordinate, it will still define a unit circle if I went over, the entire over a specific interval, and I'll kind of explain what that means in a second here. So let's kind of just go with the familiar, and then I'll talk about what happens when you switch the sine and cosine. Now, if I make these things 6, like we have here, instead of this being at, this would be the point, 1 comma 0, and this would be equal to the point negative 1 comma 0. But if I made these things 6, now these are going to have, radius 6. So this is now going to be, 0 comma 6. What happens if I change my t's to 2t's instead? Because that's what I have for this function. Now, what's gonna happen is before when I went from 0 to 2 pi, I went all the way around, and then when I went from 0 to pi, I went halfway around. But notice that if I put 2t's in here, when t is equal to 0, I'm going to be at this point, 6 cosine of 0, which is going to be, the x coordinate, and then 6 sine of 0, which is going to be the y coordinate. Sine of 0 is going to be 0, so I'm still going to get this. But when I plug in pi, this is now going to be 2 times pi, so actually it's going to draw this entire circle now. So one way you can think about this is if you have 2t here, what it's going to do is it's going to draw the thing twice as fast. So instead of having to do it from 0 to pi, let's say time from 0 seconds to 3.14 seconds, or from 0 seconds to pi seconds, now it's going to draw from, 0 to pi. Now it's going to draw it twice as fast, so 0 to pi. So it's going to traverse the entire thing. So again, remember that you can just plug these things into here to find their particular coordinates. Now, similar, if I want to do this for the sine, if I want to know this, what's going to happen here? Um, well, when you plug in 0, the sine of 0 is going to be equal to 0, and the cosine of 0 is going to be equal to 1. Now, we know that multiplying by 6 is now not going to be 0 and 1. It's now going to be 0 and 6. So what's going to happen is that function is going to start here instead. And if these two t's didn't exist here, if I went from 0 to pi, what's going to happen is instead of drawing the top half of the circle, this thing will actually draw the right half of the circle. But now, since I have a 2 pi, it's going to draw it twice as fast, so it's actually still going to draw the entire circle. It's just going to start here as opposed to starting here. So that's what happens when you switch the sine. The cosine is still the unit circle, but they're going to start at a different initial point. Okay, so back to finding this. So what we know is the length of the curve. I'm going to redefine this too. The length of the curve is the integral from a to b of the square root of, remember it was, I can call this df dt squared plus dg dt squared plus dh dt squared. And I used their prime notations last time with respect to t. Notice that we've done something previous with our r functions, is that this thing right here is something that's somewhat familiar to us. That your df, your dg, and your dh are nothing more than the derivatives of these components. And when you sum up their squares and square root them, you're actually talking about the magnitude of its velocity. So another way to actually define this length is the integral from a to b of the magnitude of v of t dt. Which is what we tend to use more often because it's a lot easier and faster to write this than this, knowing that they are equivalent. Okay, so what we can now do is we can just evaluate this function. So this is going to be the integral from 0 to pi. So a is equal to 0, b is equal to pi, and this is going to be the square root of, now, the derivative of the first squared. So the derivative of 6 sine of 2t is going to be, well, the derivative of the sine of something is going to be the cosine of something, times the derivative of what's inside, which is going to be 2. So this would be the cosine of 2t times 2, but I have a 6 in front, so 2 times 6 is 12 cosine of 2t. We got to square it. Plus, again, the derivative of cosine would be negative sine times the derivative of what's inside, which is going to be 2. So this is going to be minus 12 sine 2t squared. And then finally, we have plus the derivative of this, which is going to be 5, and I still have to square that. Now, simplifying inside this radical, integral from 0 to pi, squaring, probably a Pythagorean theorem in here, so 144 cosine squared of 2t plus 144 sine squared of 2t plus 25 dt. Now what I notice is these have a 144, so if I factor out that 144, I'm going to get the cosine squared of an angle plus the sine squared of that exact same angle. And we know that that is a Pythagorean theorem. So this piece right here simplifies to just 1. So 144 times 1 is going to be equal to 144. And 144 plus 25 is going to be equal to 169. So this is the integral from 0 to pi of the square root of 169 dt. So the integral from 0 to pi of 13 dt, and the integral of 13 is going to be 13t, evaluated from 0 to pi. So 13 times pi minus 13 times 0. So our answer is going to be 13 pi. That's going to be the length of this curve. So again, this is circular in the xy plane, but this thing goes up linearly. So really what we have here is we have a helix that goes one full revolution, and the length of this helix is 13 pi. All right, one more example, and then we'll end this. All right, so for our last example, we're going to determine the length of this vector valued function, and I'm sure you're kind of recognizing that this is nothing more than a line. Um, so the length of this line, well, line segment, because I'm cutting this off at t equals -1, and then also t equals 0. So we know that the length of the curve, L, is going to be equal to the integral from a to b of the magnitude of v of t dt. And we know the magnitude is going to be from -1 to 0. This is going to be the square root of, well, the derivatives of the functions squared and then the sum of those things. So this is going to be the derivative of this, which is just going to be 2, and then I'm going to have squared, plus the derivative of this term, which is going to be 3 squared, and then the derivative of this term, which is going to be our -6, and then I'm going to have to square it. So again, I got a constant on here. So this is going to be the integral from -1 to 0 of the square root of 4 plus 9 plus 36. So this is the square root of 49 dt, which is going to be equal to the integral from -1 to 0 of 7 dt. So this is going to be equal to 7t evaluated from -1 to 0. So the top, 0, minus the bottom. So this is going to be to 7. So if you like the videos, please consider liking, subscribing, and sharing. Thank you.